Okay, here we go, guys. Okay, welcome everyone to the Topos Institute Colloquium. Today we're delighted to have my friend and colleague and world's expert on polynomial functors, Joachim Kock. Take it away, Joachim.
Thanks a lot. I'm really happy to be back at the Topos Institute here. So the Topos Institute is right now the world center in research on polynomial functors, I think I can say. A lot of interesting developments on applications to dynamical systems and all kinds of cool applied category theory. So I feel a little bit awkward coming here to give a survey talk on polynomial functors. But maybe the picture I'll give, let's say that it's pre-pandemic. I'm not really an expert or even aware of all the interesting stuff going on at the Topos Institute. Or instead of pre-pandemic, maybe I should say pre-Topos. Okay, so I will explain a few points of the theory of polynomial functors, starting with elementary arithmetic and ending with infinity-operads. So let's start with the definition of polynomial functors. So you start with any map of sets, which we think of as a family, namely the family of the fibers. So EB is the fiber of this map over a little b. And if we have this family, conversely, we can reconstruct the map by just taking the total space to be the disjoint union of all the members of the family. So both viewpoints are very important. So from this data, we construct an endofunctor of the category of sets. It takes a set Y we sum over the base, and then we take the hom spaces. So this is the hom space from the fiber over little b down to the variable set Y. So just to stress, this is disjoint union in the category of sets, indexed by the base here. And this is hom sets. So maybe we should just start with the example when B is just a singleton, then there's only one set involved, and then we're just talking about the representable functor represented by E. Okay, so you think of this as a monomial, and altogether this is a sum of monomials, and therefore it's called a polynomial functor. Okay, let's see a more interesting example which will play a role throughout the talk. Let's look at the functor that to a set assigns the free monoid on a set, or the set of all words on this set. So to say what it is, you first have to say how long the word is. So that means you sum over the natural numbers. And once you have fixed the length, you just say all words of that length. So this is the set of all finite words in this alphabet, if you want. Okay, so this clearly has the shape of a polynomial functor. But let's see more explicitly what is the family or map that represents it. So we are summing over the natural numbers, so the base should clearly be the natural numbers. Then we need to find the total space, and what we see from the description here are the fibers. So instead of having these ends that look like they're numbers, let me put an underline to stress that this is now a set. So I need to construct a family here whose fibers are sets with that many elements. And one way to do it, let's call it M prime, is to take the set of n comma I, where I is smaller than n. Because then, for example, if we take the fiber over 7, then we're looking at all the elements, the number smaller than 7, so that's a 7-element set. And that's this fiber that we see here. So we see that this functor is polynomial, and it's represented by this map. Okay, this will play a role several times in the talk, and it's in general in the theory. So now the game is to do all the algebra we can with these polynomial functors in terms of the representing diagrams. So as an example of that, suppose I have two such polynomial functors, one e to b and another one f to c. So now I have two polynomials of this form, and I want to add them because that's something we do with polynomial functors. And you just write out what the sum should be, and then you realize that the sum is obtained just by adding the bases and adding the total spaces. So that's the sum of polynomial functors. Similarly, you can do the product. Allow me to reuse here. So what should be the product of two polynomial functors? Well, you write them out. You use the distributive law to shuffle it into this form again, and then you find that what you get is you have to multiply the bases, and then you have to do the following. You have to take fibers for this map or take fibers for this map. So more precisely, you should do this. That means you keep this coordinate fixed and look at the fiber here, or you keep this coordinate fixed and look at the fibers over here. So this is maybe not clear just from the description why this should be true. You should really just expand and see that you do get this. Alternatively, you could take the monomial case. So if these are both monomials, how do you multiply monomials? You add the exponents. And if here we have singleton, singleton, then this becomes singleton. This is a singleton, this is a singleton. So altogether we are just adding the exponents. Okay, so this is the combinatorial description of how you multiply polynomials. Okay, of course we really want to do composition of polynomials. So that's this little circ here. And I will tell you what it is, but before I do so, it's worth going to the many variable case. So let's move on to the many variable case. So in many variables, we still have e to b here in the middle, but now we have to decorate these elements by two indexing set. So what I'm going to do now is describe a j-tuple of polynomial functors in I many variables. So I indexes the variables, and this is just to give ourselves our tuple. So from this data, we get a functor not directly on the category of sets, but rather on the slice category over I, and it goes into the slice category over j. And let me tell you what it does. First, so you have something over I. First you pull it back to E. So that means you say S over star. Then you use the right adjoint to pull back here, which is a kind of multiplication. That's P lower star. And finally, you use left adjoint to pull back here. That's a kind of sum operation, and it's denoted T lower shriek. I'm now going to tell you what this is explicitly. So the input is a family of sets indexed by I. I write it like this. And now I have to tell you what it is, and it's a family indexed by j. And I said this is sum, this is product, this is some kind of duplication of variables. So altogether, the formula is the following. You sum over the fibers of this map over the j that we're looking at. Then you multiply along the fibers of this map. So that's E in the fiber over the b we're looking at. And finally, you have to put some variables here. And the variables you put here are s of e. So we're looking at an e here. So it points to a certain index in our indexing set. And that's this product of variables that we have to put here. So altogether, it's a sum of products of variables. So these are the monomials now in many variables, and we're summing them up. And then we're taking a whole tuple of them. I'm afraid I'm moving the blackboard, maybe getting a little bit out of... Is it better now? Okay, if we take I and j just singletons, then we recover precisely the one variable polynomials that we saw before. So this formula specializes to the first blackboard. Okay, now I can describe what it means to compose two polynomial functors. We want to do it completely combinatorially, meaning by manipulating these representing sets. So here's how it goes. We give ourselves two polynomial functors represented by diagrams like this. And I have to build up a diagram like this from this data. The first I do is I take a pullback here. Let me just write it like this. And let's say this map is called U, and this is called Q. The next thing I do is I use this Q to do a lower star. So that gives me something here, Q lower star of U. Then I take a pullback like this. So pullback is to take Q upper star. So this is Q upper star of Q lower star of U. And since this is left adjoint to this right adjoint, and we started here, there's a co-unit going back here. So this is the co-unit of the upper star, lower star adjunction. And now finally I take two more pullbacks. And that's the whole result. So this, and the maps here, I claim that's the composite of the polynomial functors represented by these two. So I don't expect you to see that. It requires quite a lot of work. But if you do it with ordinary polynomials, you know that it's all about combinatorics of exponents, and you move around and you use the distributive law. So why is it true? Well, there are two ingredients in seeing this. One is the Beck-Chevalley law. It says that if you go forward with a lower shriek and then backwards with a pullback, that's the same as going back with a pullback and forward with a shriek, provided the square is a pullback square. So that's what happens here. Here you do the same, but with lower stars instead of lower shrieks, but it's still true. So the difficult part is this pentagon here. So it says that if you have a pentagon square obtained in this way, U, Q, V, R, epsilon, then it is the case that U lower shriek followed by Q lower star is canonically isomorphic to epsilon upper star, R lower star, and V lower shriek. And this is the distributive law. So this is a product and this is a sum. So here we are having them in the wrong order, so to speak. And what the distributive law does is to put them back in the right order so that we have a sum, a product, and then this pullback here is something about duplication of variables appropriately. So this, together with the Beck-Chevalley, is what tells us that doing this is the same as doing directly this, with the appropriate lower shrieks, lower stars, and pullbacks. Okay, so this is how you manipulate all this algebra purely in terms of this combinatorial data. This says in particular that polynomial functor is what you get by it's generated by pullbacks and its adjoints. So here we see a little bit nicer characterization of what it means to be a polynomial functor than just saying it's something given by diagrams like this. This is rather to be thought of as a normal form for anything you can generate by these pullbacks and adjoints. And you need the distributive law to put things in the correct order. Okay, there's also a theorem which I may want to state. Yeah, where should I state it? There are several things I want to do on this blackboard. I think I want to state it here. This theorem is due to really many people in different levels of generality. And, oh no, I'm shuffling the blackboard again. It says that P is polynomial if and only if it preserves pullbacks and certain limits and co-limits. They're the co-filtered limits and they're the filtered co-limits. So right now it's not important exactly what these means and the significance of it. The important here is just that there is this intrinsic characterization of polynomial functors. But we will come back to this kind of theorem. So the names that I don't want to write because there are too many is first of all Girard in 1988, who studied polynomial functors as a model for lambda calculus. And that generated quite a lot of work by Lamarche and Taylor and later Carbone and Johnston, who all contributed to this meta or big theorem. There are several other characterizations of polynomial functors. And I should also mention Mark Webber. And I should also mention André Fayol, because although he didn't write the theorem, it is implicit in something he did in combinatorics, actually 5 years earlier than Girard. But we'll come back to that when we start to discuss combinatorics. Okay, I want to come back to the distributive law, because it's the key point in a theorem that, let me write another theorem. And this one is attributed to Tambara. It says that the category T with objects finite sets and morphisms finite diagrams like this, composed with the circ I just showed you, is the Lovia theory for commutative semirings. So this is really the theorem that tells you why, all this, we're dealing with polynomials. Polynomial rings are the free algebras, or the free semirings in this case, because we don't give ourselves negative numbers. So it's all condensed in this theorem. So Tambara himself did not actually, so he gave all the ingredients in the proof and all the arguments, but he did not state the theorem. So that was only sorted out much later, principally by Morten Bruun, who, working in equivariant topology, sorted out that Tambara actually did this. And you can also read about it in my paper with Nicola Gambino, where we explain this. Okay, I want to just show you how this distributive law corresponds to the usual distributive law for elementary arithmetic. So it really all comes down to, well, we look at this little map from a 2-element set to a 1-element set. So there's only one such map. It does like this. Let's call it M. And then we can do M lower shriek, and that will be addition in our semi-ring. And we can do M lower star, and that will be multiplication in our semi-ring. And of course, you can imagine what all the higher arity operations are, and you can also guess what the neutral for addition and neutral for multiplication will be. Now let's see, I moved the blackboard again. Now let's see what the distributive law says. So I'm going to take this one and specialize it to a few very small maps to arrive at the distributive law, which says the following: that A times a disjoint union of x plus y is x times, ax plus ay. So what do? We have to put some sets here. So this is the map M, and this is also the map M. Remember that this is the pullback. The pullback of 2 and 2, that's 4. Let me write the maps, pictures. So here is the map M. If you take the pullback of these two maps, you can choose how you do it, but I do it like this. So this is the map that joins two adjacent elements, and this one crosses a little bit. That's what you get if you take this pullback. And let me see what this one should do. It should do like this, and this one should do like this. So to be read in this direction. Okay, now let's see why this is the distributive law. So we start here.
Sorry, Joachim, there's a 3
Yes.
there. There's a 3 where you're pointing.
Yeah, thanks. So we start with something over in the slice over 3. That means we have 3 sets, and these 3 sets are A, X, and Y. If we go this way and this way, we have to remember that this is a shriek operation and this is a multiplication operation. So if we go this way, I'm reading these diagrams from bottom to top. So that means that A is just copied over, but these are added by the shriek. So this gives us this. And this is a multiplication. So here I multiply. So I get A times X plus Y. So that's this way around. The other way around, first we do a pullback, which has the effect of duplicating the first variable. So we get A, X, Y. This is a lower star operation. So we are multiplying in this crossed over way. That means that A goes to X and the other A goes to Y. That's what this one does when you use it with a lower star. And finally, this one is a lower shriek operation. So we're just summing these. And the distributive law now says precisely that these are canonically isomorphic. So that this abstract distributive law specializes to the usual distributive law when we give it as inputs these maps. So this is like the main argument that goes into Tambara's theorem. Okay, I think that's all I wanted to say about elementary arithmetic. Now we should move on to some other topics. But maybe I can ask at this point if there are any questions. Otherwise, I just move on. So the next topic is about data types. And more precisely, what's called generic data types. So data types is in the sense of programming languages like integers, list of integers, strings, and so on. Generic means data types with the property that it doesn't really matter what you put into them. You manipulate them without knowing what goes into them. And an example is the list data type. So let's take lists of elements of a set A. So that's again just it's the same thing as the free monoid like this. So this is just free monoid. So this is an example of a generic data type because you can do a lot of manipulation with lists without knowing what they are lists of. So we already saw that this is represented by this, and therefore is a polynomial functor. Now the point is that there are really many other examples. For example, the data type pair. Pair, that would be the polynomial functor y squared. It's represented by a little map like this. A two-element set mapping to a one-element set, so it's just a monomial where the exponent is 2. Triple would be the polynomial functor y cube, and so on. And now comes the point. When you build up more and more complicated data types, what you're doing is just using algebra of polynomial functors. So for example, if you want a data type that says a pair of lists, what do? Well, you just take this polynomial functor and plug it into this polynomial functor. That gives you pairs of lists. And if you want list of pairs, you do it the other way around. And if you want list of pairs or triples, well, then you combine these, but all these combinations are just algebra of polynomial functors. So this viewpoint, I think, goes back to Mainz and Arbib in the 86 book, Algebraic Approaches to Program Semantics. I believe that this book is the first time in the literature where the word polynomial functors is used for what we call polynomial functors here. They use this viewpoint to do algebra with data types. But I should say that there's another notion of polynomial functor in the literature which is a little bit different, which is rather about vector spaces instead of sets. And that goes much further back. Actually, it goes back to MacLane in 1950. So that's really old. But it's different. They're a little bit related, but they're different. So polynomial functors, in this sense, I believe that it first appeared here in this book. Now, they gave it as a curiosity somehow. They didn't really develop it. So it was developed more by Jay and Cockett in 93, maybe. So Jay and Cockett looked at polynomial functors as generic data types like this, but they furthermore require their data types to be over the list type. So that means they're looking at things like this. And this should be a Cartesian square. And they call such data types shapely types. The benefit is that I should put some terminology. So the base of a data type is called the set of shapes. So if we're talking about the list, the shape is just to say how long a list is. And then this is the set of positions. So that once you have determined the shape, you have a number of positions in that shape. So if you take the shape 7, then you have the numbers 0 up to 6 are the positions in that shape. So this is how you navigate like a cursor. You want to read something from your data type. You first say the shape and then you say the position. So Jay and Kock, they wanted to have not just a finite set of positions, they actually wanted a list of positions to make it easier to access the positions. And then I should put Abbott, Altenkirch, and Garni 10 years later, who really gave the full-blown theory of polynomial functors in the language of computer science in what they called container types. So this is really just polynomial functors, and they prove many of the things that are nowadays the basic theorems in the theory of polynomial functors. So generic data types is not enough. There's also polymorphic functions. And what are polymorphic functions? They're roughly those operations on data types that you can do independently of the input to your construction. And Jay and Kock, they realized that these are just the Cartesian natural transformation. So these are Cartesian natural transformations between polynomial functors. And allow me to erase the names now. So if you have one polynomial functor here and another here, and we think of them as data types, then a polymorphic function is a Cartesian natural transformation. And you show abstractly that to give a natural transformation between this functor and this functor, like always, the idea is to do it combinatorially, and it amounts precisely to give a pullback square like that. So what it means for shapes and positions, it means that a shape of one type must be mapped to a shape of the other type of the same size, because the size of, so the set of positions in this shape could be 7, then you are forced to map this shape to another shape of size 7. That's what this Cartesian square means. And let me just mention that the general natural transformation between polynomial functors, they are a little bit more complicated. So here we have one polynomial functor, and here we have another one. A general natural transformation is not what you would guess, maybe. It's given as follows. First you take a pullback, like this, and then you need a backwards map here. Who would have guessed? This backwards map has to do with the unit lemma, because remember the monomials, they are just the images under the contrary and unit embedding. So that's why it goes backwards. If you want a functor forwards, you need the maps to go backwards. So these play no role in my talk today because I'm a little bit old-fashioned, but they are very important in the current theory of polynomial functors in the dynamical systems and applied category theory. So they should definitely not be neglected just because I don't talk about them here. While we talk about that, maybe I should also mention a clash in terminology. In this approach to polynomial functors, especially in the work of Spivak, these are actually called positions, and these are called directions instead of positions. So that's a clash to be aware of. I don't know if you have gone as far as calling them momenta. I don't know if that's a good interpretation. Okay, among the data types, particularly important are the inductive types. In a sense, that's the only way we have to access infinite data types with inductive types. So again, the list type is an example. And if you want to define it inductively, you'd say the following. A list is either the empty list, or if it's not empty, then it has a first element called the head, and then it has the rest of the list, which is just a list, called the tail. So a list is either empty or it has a first element and a tail. So this is the inductive definition of the list type. The most basic example of an inductive type is, of course, the natural numbers, and it has a similar definition. It is given like this. A natural number is either 0, so this one here means 0, or it is a successor of a number. So I should really not write equality, I should write this as explicit equivalence or isomorphism, and the natural map goes in this way. So this one picks out 0, and this one picks out all the other by successor. So the map from here to here is successor. So this is Louvier's reformulation of the Dedekind-Peano axioms for the natural numbers. Okay, so this is just the two simplest inductive types you can think of. The general thing is the following. You start with a polynomial functor, of course. And then you generate what's called in type theory a W type. So let's call this P, and let's call the W type WP. So you can think of this as P trees. And I will tell you what P trees are. Let me just look at. Yes. Yeah, I was planning to write up a little bit of type theory, but I don't want to do that because I'm a little bit short of time. So let me just say instead that this is the. So what are these equations? They are fixed point equations because they characterize an object in terms of equation where it appears on both sides. So they are least fixed point. And this is informal parlance for initial algebra. So what this really is, it's initial algebra for the polynomial functor 1 plus p. P is the polynomial functor represented by this data. So what does it mean? Let's take the case of ordinary trees, although I'm cheating a little bit here. It says that a tree is either the tree without nodes, or it has a node which is then, you can take the node closest to the root, and then you have to give a family of trees indexed by the edges of this node. So if this is the whole tree, then you see that tree here. So what we are saying is that WP satisfies the equation 1 plus P of WP. That's what this equation says. So the notion of W type in type theory is due to Martin Löf. And I should mention, so this equation here is Moerdijk and Palmgren, who started this whole idea that W types are precisely polynomial functors in this precise sense. So these are sort of a very general class of inductive types that you use in program semantics. There are more general things, but then it's not directly covered by polynomials, although polynomials still play a role. I just want to continue this by noting that there's also a purely combinatorial description of the P-trees. And maybe surprisingly, that involves, again, polynomials in many variables. So let me erase here. and keep the picture. So let me first say what a tree is. A tree is a diagram like this, where A is the set of edges, N is a set of nodes, so to every node you can assign the outgoing edge of that node. M is the set of nodes with a marked incoming edge, and you can return that edge. So altogether this describes all the data of the tree, and you see that it's the shape of a polynomial functor. For such a thing to be a tree, you need some axioms, and some of the axioms state that these should be injective, and there are a few more axioms. So a tree is that. And now we can say what a p-tree is. A p-tree is just a tree decorated by the polynomial functor p. So down here we have our polynomial functor, and we need to decorate every node by an element in B, and we need to decorate all these node edge incidences by elements in E, and this should be Cartesian. And what it means is that if this node has 7 incoming edges, it must be decorated by a little b whose fiber is of cardinality 7. And not only has cardinality 7, there's in the pullback there's given an explicit bijection in this labeling. And let me just put the one variables here for completeness. So this is a purely combinatorial description of what it means to be a p-tree without induction or anything. Okay, now we are already in the mood for combinatorics, so let's go to combinatorics now. And also back in time, because now we go to the theory of species invented by Joyal in 81. So here's the definition. A species is a functor from the groupoid of finite sets and bijections into the category of all sets. So F. And it's a tradition to denote it with square brackets like this. So you should think of this as the set of F structures on S. So F was something abstract, but just by being a species, it defines a notion of F structure. But to give a concrete example, this species could be the species of linear orders, so that you to every set assigns the set of all possible linear orders on that set. That's an example of a species. In that case, if the set has n elements, then of course this set over here will have n factorial elements. So that's an example of a species. So Joyal invented this in order to give a categorical foundation for the use of generating functions in combinatorics. So in enumerative combinatorics, what people have done for a very, very long time is given some structure, which actually is a species, even if you don't know it's a species, you write down a generating function for it. That's a power series. And then you manipulate power series with all the techniques you have, algebraic or even analytic. And when you have your result, you just give it back to combinatorics and you have counted something. So it seems a little bit roundabout that you should go all the way to power series and come back. Can you not do that directly on the combinatorics? And Joyal showed how you can manipulate all the operations of power series can be done at this level. So that's a very powerful technique in combinatorics. But there's also a direct way to actually see these generating functions. Because if we have a species F, then we can take the left Kahn extension along this inclusion I. So note that this is not full. because here we only have groupoids, only bijections, and here we have all maps, so it's not a full inclusion. And we call this F tilde. So this is left Kahn extension along I of F. So this is the model for the generating function, because there's a following explicit description. F tilde of y is, first you sum over the connected component of b, so that's just natural numbers. Then you evaluate your species on that finite set. Then you take y to the n, and then you divide out by the group action of the symmetric groups. So it acts diagonally here by permuting the factors, and here by functoriality of f. So this is called an analytic functor. And this is Joachim 84. So it looks very polynomial. It's a sum of monomials. But there is a crucial difference, namely that you have these denominators. And these denominators are factorials, and of course that's why they're called analytic functors. So Joachim proved the following theorem, which you can recognize as very similar to Girard, Lamarche, Taylor, Carboni, Johnston, Weber, namely that F is analytic if and only if it preserves pullbacks weakly and co-filtered limits and filtered colimits. So the difference is in the word weakly here. So what does it mean to preserve a pullback weakly? So a weak pullback is one that has a property similar to the usual pullback, but instead of demanding a unique map here, you just demand the existence of a map. That's a weak pullback. And to preserve pullbacks weakly means that it sends pullbacks to weak pullbacks. My computer said beep. Was it something?
Nothing from us.
Okay, sorry about that. So you can see that it's the same theorem as the one I quoted earlier, but it only preserves pullbacks weakly. And this is precisely because of these group actions. More precisely, group actions or quotients by quotients by group actions are problematic when the action is not free. So this is a slogan that it has taken mathematics quite some time to really learn to deal with. I mean, maybe it has been known for a very long time that this is the case, but the fix is rather recent. So what's the problem? The problem is, so suppose you take a one-element set and you act on it by a group and you take the quotient, so a non-trivial group. Then this quotient as a set is of course just singleton again. But this is a bad colimit you're taking here. Let's take an example, let's take the integers. This is a bad quotient. The real thing is you should get the following. You should get the classifying space of the integers, which is a circle. So this is no longer a set. Now it's a groupoid. So the really good colimits of diagrams in sets are not necessarily sets. They could be groupoids or higher groupoids. So that's actually the origin between the discrepancy between analytic functors and polynomial functors. So you see here that a polynomial functor will preserve pullbacks strictly and all that, so it is in particular analytic. So that's a subclass of the analytic functors. More precisely, there is actually a name for that in combinatorics. You say that a species is flat if the sigma n actions are free. And there are many combinatorial structures that are flat. Generally, whenever you have something rigid like planar trees or linear orders or things of the sort, then the group actions are actually free. And that means that this one actually can be absorbed into here and you end up with a polynomial functor. So flat species is polynomial functor. I'm glossing over some finiteness conditions. Sorry about that. Okay, but now there's a discrepancy between polynomial functor and analytic functor. It looks like it's something that ought to be the same. And the fix is to go to a homotopical context. So the theory of polynomial functors and the theory of analytic functors, they generalize to infinity groupoids. So you don't need to know here what an infinity groupoid is. It's just an algebraic setting for, it's a homotopical world where you have the elbow room to do the correct colimits. So this is joint work with Gebner, Haugseng, and myself. So the reason this generalizes is because it is an elegant theory. I mean, the fact that you don't have to look at the polynomial functors themselves, you can look at their representing diagrams and do the theory at that level. That's what helps you to generalize from sets to infinity groupoids. And then become equal. Meaning that the weak preservation of pullbacks that we saw in the analytic functors at the level of sets, that's really just a deficiency of the category of sets, that the category of sets does not have the appropriate colimits. So once you generalize or lift it to infinity groupoids, that weakness of preservation of pullbacks goes away. And analytic functors are just to preserve pullbacks. But of course, then pullbacks means homotopy pullbacks. That's all we have in the homotopy world. So that means preservation of pullbacks here, preservation of pullbacks here, they become the same thing. So this is an example of this phenomenon that things become nicer when you pass to the infinity world. Some of the quirks of the category of sets get resolved. To finish, I just want to say that operads, so operads come from topology to parameterize or describe up to coherent homotopical algebraic structures. So they can be described as monoids in species or monoids in analytic functors under the composition product. This is an observation by Kelly in 72, except that he didn't know that it was analytic functors. That's, I mean, maybe I should say Kelly and Choyal combined give you this one. Okay, so now you can guess what happens. It's not completely, I mean, it requires a lot of work, but there's also something called infinity-operad. And that's now, so this is analytic monads. So now we get analytic or polynomial. Monads, but I should put an infinity somewhere. So let me see how I'm doing on time. Can I have 2 minutes, because then I would like to write a statement so that I can finish my talk with the word topos. Is it okay?
Yes, it is okay and good.
Yeah, let me take the operads. So if you look at the category of polynomial functors, and we are only looking at the Cartesian fragment, well, I have been suppressing finiteness conditions, but here I really want to put it just to not tell you lies. So this means finitary polynomial functors. At the level of representing set, it means that this map has finite fibers. So this is not a topos. For example, it doesn't have a terminal object. EG does not have a terminal. So now if we do the infinity version, and I'm still only talking about the Cartesian fragment, and I still put this finiteness condition, then it has a terminal. And that terminal object is the exponential. So in terms of species, it's just this one. That's the exponential. And now that's terminal. It should have been terminal all the time, but the problem with colimit prevents this from being true in the category of sets. But if you go to a homotopical setting, then it is a terminal. So that's very nice. And that's, I mean, of course, that does not prove it, but it is true that this is a topos. And of course, I need infinity here. And that was the last word of the talk.
Thank you. Thank you, Joachim. Yeah, there's many people here because we're having a polynomial functors workshop this week, so we really appreciate this talk.
Thanks.
Yeah, thanks. So questions, if people have questions, you can raise your hand or just unmute yourself to ask. Let's see.
I don't know. I may have.
Go ahead, Andre.
I may have a question.
You next. Yes, please. You have one, and then we'll have one from in here. Andre Joyal, you can go.
Yeah. Okay. Thank you. Joachim, that's a very nice talk. Very beautiful.
Thanks.
Like always, your talks are always very beautiful. I have a question that just came into my mind about, in combinatorics, we like counting, and so we have natural numbers and integers, right? and there is a power series associated to a species. And this power series has coefficient not in set, but in integers or things of the sort, right?
Yes.
So we may want to have something like this for these generalized species where the coefficients are in your theory with Gepner and Hodgson. They are homotopy types. I mean, they takes values in homotopy types. So we would like to have numbers associated to homotopy types,
Yes.
and etc. etc. And can you comment about this? Is there some numbers that you would like to?
Yes. So, I mean, there are two ways you can get around it. Either you can still have your coefficients to be integers, so you take values in sets, and you can keep track of that with this little thing here. Instead of preserving filtered colimits, you can preserve sifted. I should actually say sifted colimits here. In that case, you still want your coefficients to be integers. But you can also open it up and allow any homotopy type to be a coefficient. In that case, you need some kind of cardinality for those homotopy types. But as you know, that can be done. So there's a infinity groupoids. I should make them suitably finite. And I put a pi here because technically it's called pi finite. Now you can, there's a cardinality functor from here to here that is well behaved for all the operations involved, so that you can model a power series with positive rational coefficients in this way. So the basic example is if you have the classifying space of a group, and if the group has n elements, then the cardinality of this one is 1 over n, as you know. So there is a possibility to work out the theory with these coefficients instead of whole numbers. I don't know if that answers your question. I'm sure you know this, so that's why I'm in doubt.
Yeah, it does. Maybe there are many ways to interpret my questions, but here the numbers are actually, you have replacing integers by rational numbers, which is nice. But
Yes.
I was thinking, wonder if one used some kind of K theory of group of spaces, maybe Waldorf K theory, something I don't really understand. But I wonder if one could also maybe use some K theory.
Yes, so that's a question of a lot of current research. So it's about actually getting also the negative rational numbers, or even the negative integers. And some kind of K theory should be introduced to invert and get hold of the negative numbers. But it is not at all easy, and I don't think there's a satisfactory answer at this point. I'm very interested myself in this particular question.
Okay, thank you. That's yeah, thank you.
Great. And we have another Andre here in the office, so go ahead.
Yeah. My question is maybe basic, but
Can you hear him? Can you
Yes, no, I cannot hear if anybody is speaking.
hear? Oh, someone was speaking, so he'll come up, I guess. Okay.
So in programming / proving in MLTT with Poly, the equalizer map needs a co-equalizer on directions, which in set requires quotients, and quotients are hard in set, but they're nice in homotopy type theory. Does this have anything to do with the polynomial / analytic distinction or discrepancy? Did working in cubical type theory mean I was somehow working in infinity groupoids or something?
So I heard the word cubical, that I don't know about, but it's true that the problems you have in classical data type theory, where often you would like to have symmetries on your data types. And you cannot do that in the classical polynomial setting. But in the homotopical polynomial setting, you can precisely do that. And this was also observed by Håkan Gülterud, who introduced a notion of containers with quotients. But the polynomial functors over groupoids is the nice language to deal with that, certainly.
Okay, thank you.
Okay, I think we have time for one more question if anybody has one. Yeah. Okay, we have one more in here.
Hi, thanks. Really enjoyed the talk. I just had a clarification. When you said that the monoids with respect to composition for analytic functors are operads, and then the in the infinity groupoid setting, they're infinity-operads. Is that still with like Cartesian maps, or is that just you take all the natural transformations?
That is with Cartesian maps, yes. Everything takes place in the Cartesian context where the natural transformation are Cartesian, and in particular the monad multiplication is Cartesian. However, if you look at classical operads as monoids and species, then you should use weak pullbacks or weakly Cartesian natural transformations, as Joyal did in his paper on analytic functors. So in that case, you have to say analytic functors with their weakly Cartesian natural transformations. And then you take monoids in there, and they are the analytic monads, and they're the operads.
Okay, cool. And this is still finite, right? I know you elided the finitary.
Well, yes. I was very sloppy about that. If you want operads, you definitely have to say finitary polynomial functors. And in the infinity context, you even have to say finitary discrete. But I mean, that's something you can juggle with depending on what notion you want to study. So you could potentially want something with, I mean, you can open up the class of colimits you want to preserve, filtered or kappa co-filtered or sifted. There are many options, truncation levels and so on.
Gotcha. Thank you so much.
Okay, so why don't we stop the live stream here and the recording here, and thank Joachim again. Thank you.
Thanks. Thanks.
Okay, so I'm in the process of stopping the recording and the live stream and all that. If anybody has any questions they want to ask, if you have another minute or two or so.
Oh yes, of course.
I put a